Hey, it's Matthew Todd and welcome to the next lesson in Module 3. In this module so far, we've talked about what we mean by unit testing, in terms of what we actually mean by a unit, and seeing how we can define a unit from a couple of different perspectives. We've also talked about refactoring, what we mean by this and why we need to do it, and we've seen how different levels of refactoring can have an impact on the units that we have in our application. So in this lesson, I want to talk about and demonstrate how testing for purpose can make refactoring much safer, something you're confident to do and happy to do. Refactoring is something I found a lot of developers typically put off, usually out of fear, either a fear of breaking something or a fear it will become a very time-consuming task, and therefore make them appear unproductive. And this does mean that small to medium refactors get put off, and solutions that are no longer the best fit get built on top of, until you get to a point where a larger refactor then becomes required. So a lot of people will struggle with refactoring, and it may seem counterintuitive, but they actually struggle more if they have tests in place. So why is this? Surely tests are there to help us, right? They're here to catch issues when we break the code. So tests should help us with this refactoring process. Well, not necessarily, because with the wrong test approach, with the wrong test structure in place, it can actually be very easy to end up with a more rigid, brittle test structure. And then when you do perform refactoring, you're left with a number of test failures and breakages that you then have to fix. And this means that refactoring with that kind of test setup in place actually causes significantly more work for you. You're left with many tests to fix and clean up, and in many cases with anything other than a trivial refactor, it's not even obvious what the test fixes should be, whether any particular test is still valid, what test setup or input is relevant or could be affected by your refactor, whether the assertions are still valid, and also whether the assertions are even complete and verify everything you now need them to. If you aren't put off by the amount of work this would involve and decide to go for it, you still tend to focus on making the tests unbroken and pass, rather than ensuring the behaviour remains correct. And this is where testing for purpose comes in. In the last module, we saw how TFP provides a benefit when writing the unit tests and when taking a test-driven approach. Because of the focus on behaviour rather than actions, it forces us to adopt a mindset where we're producing very small, precise tests. Each test has a very clearly defined purpose, and we can immediately see from its name what purpose it serves, what single piece of behaviour it's verifying. We can also see from the small test body exactly what the test input is, what test input is relevant to that particular tester behaviour, and we should see a very small set of assertions and therefore understand exactly what it looks like to verify this particular piece of behaviour. So let's look at a more concrete example of a refactor now, how testing for purpose can help us, and also talk about what it might look like if we didn't take this approach. So as a demonstration, I want to return to a reverse Polish notation calculator from Module 1. So I'm showing this from a Java viewpoint, but again the principles, strategies are the same, regardless of the implementation language, or even approach taken within the same language. If you want to check out the JavaScript version of this, then see the additional resources section below. As you can see with the Java version, I've made some minor test changes to split our test into separate files with test setup methods, where each file represents testing the calculator from a different initial state, as we talked about before. So you can see I've extended the calculator and added tests and implementation to cover the subtract operation, as well as the addition that we had before. So I've taken the exact same test approach and implementation approach as we did with the add method. So I've taken a test-driven approach using testing for purpose to build up the implementation. The implementation I went for is the simplest one, working in the same way as the addition, so I haven't attempted to factor out any common code at this point. So the stack manipulation is in the subtract method as it was with our add method. If TDD is about red-green refactor, then we've got to the point where we've tested two operations, addition and subtraction. We've gone through multiple red-green cycles, so now we can look at the refactor. So depending on your application, this refactor could come immediately after implementing the simpler solution, as in this case, or it could be at some future point where you decide that before continuing, before adding more features, or operations in this case, you'd like to refactor before you do that. It doesn't really matter at what point in time you decide to do this, the approach is the same. So I want to demonstrate a refactor, as we talked about before, where we're changing the structure of the units that we have. I don't just want to extract some common code and change the internal structure of our calculator. I actually want the calculator to be concerned only with stack manipulation, and then the application of operations, but the operations themselves should live elsewhere. So the approach I want to take with this is one where we're going to leave the calculator alone as much as possible. We're going to avoid making any breaking changes to the calculator, and we're going to try and do that until the last possible moment. So as we said before, our operations are now going to be external to our calculator, and in order to achieve this, I want to create an interface that represents an operation class. An interface that our add and subtract operations will implement. So I'm creating a simple interface here, operation, with a single method calculate. Hopefully not too surprisingly, it takes two float values and returns a float, the return value being the result of the calculation. But again, our calculator isn't going to make use of this yet. I'm going to delay this until the last possible moment. So now I'm going to proceed with the actual operations themselves. So I want to implement an add operation and a subtract operation, starting with the add, and because we're taking a test-driven approach, as we did before, we'll start with a test for this, a failing test. So we'll create a test class as before. In this case, the actual test we're going to add is going to be very simple. In fact, there is only one piece of behaviour that these operations will have, because their only responsibility is to perform this calculation. Obviously, in a more complex scenario, you would have many behaviours, and you would use testing for purpose, as we have done before, to implement each individual test. Each individual test of behaviour will be a different test in this class. So we'll start by trying to instantiate the operation we want to test. And as before, we've got our first failure. In this case again, a compilation failure because the operation doesn't exist. So we'll use the IDE to create this. It doesn't implement the methods on their interface, so again this can be done in the IDE. And for now we'll leave the default implementation, leave it returning 0. So now I'm going to call calculate with some test data. And I'm going to add an assertion to assert that the result is the correct result of this calculation. So in this case 2 plus 3 is 5. Run the test, we see it fails as we expect, because we're returning 0. So again, switching to the implementation, we change this to perform the correct calculation, and our test should now pass, which it does. So we've gone through a couple of red-green cycles there to implement that. Now before looking at the calculator itself, I want to do this exactly the same thing for the subtract operation. So again, I'm going to start with the test, subtract operation test. Going to follow the same red-green cycle we did with the add operation. So we'll start by trying to instantiate it. It doesn't exist, that's our first failure, first red phase. So we use the IDE to create the class and implement the interface, again sticking with the default implementation to start with. So now I can attempt to call calculate on this operation, call it with some test data, and assert that the result of the calculation is what it should be. In this case, 8 minus 2 is 6. So running our test, hope that it fails, which it does, because we're returning 0. So now switching back again to the implementation, we'll fix this like so. Running the test again, we see it passes. Okay, and again I've left our calculator implementation exactly as it was before. Now if we return to the tests, remember that we are testing for purpose, and this strategy means that every single piece of behaviour has its own test. So as part of refactoring, where a refactor does change the structure, the behaviour of our application hasn't changed, just that these different pieces of behaviour may have moved. So what we have to do when refactoring is look at our behaviour-oriented tests and decide which behaviours still remain in the calculator and which ones are external to the calculator. We're not creating any new behaviours here. All the behaviours that we had before still live somewhere. So the process I'll go through now is starting with the simplest form of our calculator, in this case the new calculator. I want to go through each test file one by one and add relevant tests to this to test our new way of using these operations. So looking at the new calculator test, we can see that from our previous tests an add operation isn't allowed in a new calculator, same as a subtract operation. So thinking about refactoring to extract the operations, this is still a behaviour that does exist in the calculator, but it's no longer related to a specific operation. This behaviour should apply to any operation. So I'm going to add a new test method here, leaving the existing ones exactly as they are for now. And I'm going to test that invoking an operation is not allowed on a new calculator. So copying the subtract example as a starting point. In this case, rather than calling subtract, I want to try and invoke an operation. So here we go, calculator invoke operation. In this case, I'll just create a null instance of an operation. We don't need a valid one. It shouldn't get as far as needing a valid one if it throws the error. So we've got a first red phase again. This invoke method doesn't exist, so we can create this. Again, for now, we'll just leave the simplest implementation possible. Running our test, we see it fails as we expect because we're not throwing an exception of any kind. So back to implementation. Again, we'll go with the simplest implementation needed to make the test pass, so we'll just throw the empty stack exception. Similar way we did before. So we're taking a test-driven approach, going from red, green, until we've got the desired functionality that we want. Okay, so this test now passes, as we expect. So now we can move on to our next test. So going to the calculator with a single value on the stack test this time. In the same way, the add and subtract operations weren't allowed in the calculator when there's a single value on the stack, because we need there to be two values. The same thing is going to be true for a general operation, rather than the add or subtract specifically. One reason for performing this refactor is to make the calculator only concerned with the stack-related things and have the operations outside. Therefore, the calculator doesn't need to know about any specific operation. So adding our test here. Again, we want to make sure it throws the empty stack exception when we attempt to invoke the operation when there's only a single value on the stack. Given the simple implementation we've got at the moment, we know this will pass. Running the test, we see that is the case. Next, moving on to the tests that are related to the calculator when there are two values on the stack. We can see with the test we've got for both add and subtract, we are testing two different behaviours here in each operation. When we apply each operation, we're testing the stack manipulation, and we're also testing that the calculation is correct. So here we're just testing the calculator, so we don't need to worry about testing the operations themselves are correct because we've already done that. We've done that in their own unit tests. But what we do need to test in this file is the behaviour relating to the calculator itself. And this is the stack manipulation. The stack manipulation remains a responsibility of the calculator, so we can take a more general case of the behaviours that we've tested above with add and subtract. We can make sure that when we do invoke an operation on a calculator, the stack size is what we expect it to be. So when we invoke the operation with two values on the stack, we should end up with a stack with a single value on it. Now in this case, because we're actually invoking the operation, we do need there to be a valid operation rather than null. So in this case, we'll just use Mockito to create a mock object. We'll create a mock of the operation interface. We don't care what it returns, it doesn't need to return a value that we're testing here, because we're purely concerned about a single piece of behaviour, which is the behaviour that lives in the calculator that relates to the stack manipulation. So running this test, it fails as we should expect, because we're just throwing the empty stack exception. So now we can change this, improve the functionality here, improve it in such a way that the tests we've got now all pass. So we're removing a couple of values from the stack and just pushing the default value of 0 back onto the stack. So running all of our tests, we see that all of our tests are passing. So our test relating to what happens when we try and invoke an operation with a new calculator. With a calculator with a single value on the stack, these tests are still passing. And a new test relating to 2 values on the stack when we try and invoke the operation, a new test is also passing. A test where we tested the stack size is manipulated. So next, looking at our existing tests, we see there are a couple of tests of the same type of behaviour, one relating to add, one relating to subtract. And what this is doing is it's making sure that the calculation has been performed and the result of that calculation is on the stack. So the first behaviour was relating to the stack size, the second one was relating to the calculation that's on the stack. Because of the way we implemented it before, we needed separate tests for add and subtract, because the calculations themselves were in the calculator class. In this case, our operations are now external to the calculator class, but we do want to make sure that our operations are invoked when we ask them to be. So in this case, in our test, we set up a mock object as we did before, but this time we want to make sure that the operations calculate method was invoked, and it was invoked with the right arguments, with the values that we put on our stack in our test setup. So running this test, it fails as we expect because we're not even calling this method. So now we've got a test failure, we again switch back to the implementation. This time we need to change it to retrieve the values from the stack. And call our operation calculate with those values. Note we're not pushing the result onto the stack at this stage, because that's not actually required by the test that we have at the moment. So our test will pass if we simply call this. Okay, so now we've verified the behaviour relating to calling our calculate method, calling the calculate on our operation. So now we can add another test where we actually make sure that the result of the calculation is pushed onto the stack. So currently we've tested the stack size changes as we expect. It's the first piece of behaviour. The second piece of behaviour that we want to verify is that the calculate method is called in the operation. So finally, we need to make sure that the result of this operation ends up on the stack, because that's a piece of behaviour that needs to live in the calculator. It needs to remain in that invoke method. So adding a test for this. Note here, we do have a mock operation, but we're using it more like a stub in this case. So basically we're saying when we call operation.calculate with any float values as arguments, then return a value of 2. So we're not actually verifying that the calculate method is called with the right arguments, because we've already done that in another test. And that's the key thing when using test doubles, using the testing for purpose strategy, is each piece of behaviour should only be verified in one place. So we don't want to be verifying it again in this test. Hence the looser constraints here when we call operation calculate. All we needed to do here is to return a known value, and that's the value that should end up on the stack. So here we invoke the operation, get the stack back, and make sure that the value on the stack is the value that we returned from the calculate. Running our test, we see it fails as we expect, because we're still pushing that default value of 0 onto the stack after calling calculate. So again, we can switch back to the implementation. Change this, so rather than pushing 0, we push the result. Running our test, we see that it now passes. Onto our final test class, where we test a calculator with 3 values on the stack. We can see here we're testing applying the add operation to a calculator with 3 values, results in the first value on the stack unmodified, plus the result of the calculation. So again, this is a behaviour that still lives in the calculator, doesn't live within our operations. So add a new test for this using our calculator invoke method, where we invoke any operation. This behaviour should still hold true. So again, we use a mock operation for this, and again we don't care what values operation calculate is called with, because we've verified that's called with the right arguments elsewhere. So we'll return a value of 10. Copy the assertions from the test above. And we see that it does indeed pass as we expect. So it's giving us confidence in our code having the behaviour that we expect of it. Now remember, we haven't actually made any breaking changes to our calculator. So at the moment our calculator is capable of working in the old way, plus the new way. And whenever I perform any refactor, I always try and aim to get into this situation if possible. I try and avoid breaking changes for as long as I can. And looking at the test changes that we've made, we can see that each piece of behaviour that we're testing relating to calling add and subtract in the calculator directly is also a piece of behaviour that we're verifying in the general way when we call calculator.invoke. So the final thing we can do is to remove the actual add and subtract methods from the calculator class itself. This will complete our refactor. So we'll delete these, leaving just the invoke method. Now we can see we've got a number of compilation failures as we expect. And the thing to do now is, looking at the compilation failures, which are in our test code, is to verify that the behaviour that's being tested in the methods that are no longer compiling, verify that these pieces of behaviour are still tested somewhere. Because remember, refactoring doesn't change the behaviour of the application, it just changes where that behaviour lives. So using testing for purpose means that our tests describe distinct pieces of behaviour, so therefore for every test that we had before that no longer compiles, there should be a corresponding test using the invoke method or using one of our new operation classes that does compile and run and pass. So as we go through here, before deleting these methods that don't compile, we just have to ask ourselves whether the behaviour that this is testing is still tested and it's being tested in the right place. So in this case, where we have add and subtract being called and we're testing error conditions, or where we're testing stack manipulation, these things are still performed by the calculator, so should be in one of our calculator tests. And where we have the test methods that are actually verifying the result of these calculations, we know that we have add operation test, subtract operation test, that are verifying our new operation classes are correct, are performing the right calculations. So from looking at these failures, from looking at the behaviour being tested, both in the tests that are not compiling and in our new tests, we can be sure that all of the behaviour we had before still exists because it's being tested in its own distinct test, in its own test method. This might live in a calculator test class, or it might live in one of our new operation classes, but there's a one-to-one relationship there. All the behaviour is being tested, so we have confidence that our refactor is complete. So that's it for now. In this lesson, we've seen how using testing for purpose initially, making a test behaviour driven, makes the decision about how and what we want to test when refactoring much simpler. Focusing on the behaviour means that when we do refactor, we just have to think about how our refactoring is affected where each type of behaviour now lives. If we'd gone with the approach most developers take, focus on the action, the methods in our unit, then the behaviours and verifications of these behaviours would have been less clear, likely distributed between our tests. So we'd had to unpick those, which would not only have been time consuming but also risky. It's easy to miss things this way. So I'll leave it here for this lesson, and I look forward to seeing you in the next lesson, where I'll set your refactoring exercise based on your previous work so that you can put this into practice in a safe environment.